Have you ever wondered what's really happening inside those tiny components that power, well, basically everything in your digital life? Today, we're going to crack open the capacitor and really understand the incredible forces and the energy that's packed inside. Let's jump right in. So we're going to tackle two really cool questions. First up, do the plates of a capacitor actually, physically pull on each other? Spoiler alert. Oh, they absolutely do. And second, we've got this famous energy puzzle. When a battery charges a capacitor, it seems like half the energy just disappears. Poof. Gone. So where does it go? Let's figure it out. Okay, let's dive into that first idea, this hidden force. We usually just think about capacitors storing charge, right? But underneath it all, there's this really powerful mechanical tug-of-war happening between the plates. Now, this is a super important point, so stay with me. To figure out the force pulling on, say, the negative plate, we only look at the electric field created by the positive plate. It's kind of like this. You can't lift yourself up by pulling on your own shirt, right? A plate can't create a force on itself. The force has to come from the other plate's field. So the key to all of this is the formula for the electric field from just one of those big charged plates. It's E equals sigma over 2 epsilon naught. Now, don't let the letters scare you. Sigma is just the surface charge density. That's the total charge, Q, spread out over the plate's area, A. This formula, especially that little 2 on the bottom, is the secret sauce for everything that's coming next. All right, let's put it all together. It's actually pretty simple. We start with the most basic force equation from electrostatics. Force equals charge times electric field, or F equals Q. The Q here is the charge on the plate feeling the force. Then we just take our expression for E from the last slide and plug it right in. A little bit of algebra, and boom, we get our final result for the force between the plates. This one's a keeper, so make a note of it. Now that we know the total force pulling on the plate, the next logical question is, how is that force spread out? And that brings us to a really neat concept called electric pressure. So what's the real difference between force and pressure? Well, think of it this way. Force is the total oomph, the total pull measured in newtons. Pressure is that same oomph concentrated on a certain area, measured in pascals. It's like being pushed with the palm of a hand versus being poked with a needle. Same force, very different pressure. And getting to the formula for pressure is super straightforward. We just start with the definition. Pressure is force divided by area. So we take our big force formula from before, divided by A, and look what happens. We get Q over A, which is just our old friend sigma, the charge density. A little tidying up, and we get this beautiful, elegant expression. It tells us that the electric field is literally putting a squeeze on the plates. Okay, so we've got force, we've got pressure. Now let's get to the main event, energy. Because when you store energy in a capacitor, what you're really doing is work. You're fighting against that very electric force we just calculated. Let's see how that adds up. I want you to imagine building up the charge on a capacitor, but not all at once. Imagine we do it one tiny little packet of charge at a time, a little dq. Each time we move one of these little packets over, we have to do a little bit of work. Why? Because there's already some charge Q sitting on the plates, which creates a voltage V, and that voltage pushes back. The work we do is just that voltage times the tiny charge we're moving. And this is where a little bit of calculus becomes our best friend. That tiny bit of work, dW, is just V times dQ. And since we know V equals Q over C for a capacitor, we can say dW equals Q over C dQ. Now, to find the total work, to charge it all the way from 0 up to the final charge Q, we just add up all those tiny bits of work, which is what an integral does. The integral of Q is just Q squared over 2. And when you evaluate that from 0 to Q, you get the final stored potential energy, U equals Q squared over 2C. Beautiful. So here it is, our first big-time formula for the energy stored in a capacitor. You can see right away that the energy is related to the square of the charge. That means if you double the charge, you actually get 4 times the energy. But hey, what if you don't know the charge, but you do know the voltage across the capacitor? Well, no problem at all. We just use the fundamental definition of capacitance, Q equals CV. We substitute that into our first energy formula, a C cancels out, and we're left with this second incredibly useful version. The stored energy, U, is 1/2 CV squared. Honestly, this is probably the one you're going to see and use the most. We've seen how the energy gets stored, but where does it come from in the first place? Well, that's the battery's job. The battery is like the engine in this whole operation, the thing that pushes the charges around and actually does the work. When it comes to figuring out the work a battery does, there's one really simple rule to remember. Just follow the positive charge. If positive charge is flowing out of the positive terminal, the battery is supplying energy. If positive charge is flowing into the positive terminal, it's absorbing energy. It's really that simple. So in our case, when we're charging a capacitor, positive charge is flowing out of the battery's positive terminal and onto the capacitor plate. This means the battery is doing positive work. It's pumping energy into the circuit. And the amount of work it does is simply the total charge that moved, Q, times the battery's voltage, V. And just to be thorough, let's think about the opposite case, like when you're charging a rechargeable battery. In that situation, positive charge is forced into the positive terminal. The battery is doing negative work, which really just means it's soaking up energy from whatever is charging it. But for our capacitor problem today, we're all about that first case. Okay, theory is awesome, but let's make this real. It's time to take all of these ideas, put them together, and walk through a classic problem with some actual numbers. All right, here's our setup. Super simple circuit. We've got a 2 microfarad capacitor, a 3-volt battery, and a switch. So the question is, what happens when we flick that switch? What's the final charge? How much work does the battery do? And how much energy actually gets stored? First things first, let's find the total charge that ends up on the capacitor. For this, we use our good old friend Q equals CV. That's just 2 microfarads times 3 volts, which gives us a final charge of 6 microcoulombs. Easy enough. Okay, next up, how much work did the battery have to do to move that charge? Well, we just use our battery work formula, W equals QV. The total charge that flowed was 6 microcoulombs, and the battery voltage is 3 volts. So the work done by the battery is 18 microjoules. Now keep that number in your head, 18 microjoules. And now for the final piece of the puzzle, how much energy is actually stored inside the capacitor? Let's use our U equals 1/2 CV squared formula. That's 1/2 times 2 microfarads times 3 volts, squared. You run the numbers and you get 9 microjoules. Wait a second. The battery did 18 microjoules of work, but the capacitor only stored 9. Where did the other half go? And here's the big reveal, the solution to the mystery from the very beginning. Look at the numbers. The battery put out 18 microjoules of energy. Only 9 of those microjoules made it into the capacitor as stored potential energy. The other 9 microjoules, exactly half of the total, was lost as heat. As the current flowed through the connecting wires, their natural resistance caused them to heat up, so the energy didn't vanish, it was just converted into a different form. And that leaves us with one last really interesting thought. This 50% energy loss isn't a fluke. It's what always happens when you charge a capacitor with a simple battery. So that begs the question. Is there a better way? Is it possible to charge a capacitor more efficiently, to lose less than half the energy as heat? That's a great little puzzle to think about. Thanks so much for watching.